Graphs are powerful tools in computer science and mathematics. They allow us to represent relationships between objects. These objects are called nodes or vertices. The connections between them are called edges. Think of a social network like Facebook. Each person is a node and their friendships are the edges. The study of graphs is called graph theory. It helps us understand and solve problems related to networks. These networks appear everywhere in our lives. Examples include transportation systems, computer networks, and even social structures. Graphs come in different flavors. They can be directed or undirected. In directed graphs, edges have a direction, like a one-way street. This indicates that the relationship only works one way. In undirected graphs, edges are like two-way streets, representing a mutual connection. Understanding graphs and their properties is crucial for many applications. These include finding the shortest path between two locations, identifying influential people in a social network, and optimizing resource allocation in a network. This is where flow networks come in, offering a specialized framework for analyzing capacity-constrained networks. Flow networks build upon the foundation of directed graphs. Imagine a network of pipes carrying water from a source to a sink. Each pipe has a certain capacity, limiting how much water can flow through it. Flow networks help us model and analyze such systems. In a flow network, we have a source node where the flow originates and a sink node where the flow ends. Each edge has a capacity, a non-negative value representing the maximum flow it can handle. Our goal is to find the maximum amount of flow we can send from the source to the sink without exceeding the capacity of any edge. The flow through an edge is governed by two essential rules. First, the flow cannot exceed the edge's capacity. Second, for every node, except the source and sink, the total flow entering the node must equal the total flow leaving it. This is known as the conservation of flow principle. Flow networks are incredibly versatile for modeling real-world scenarios. They can represent transportation systems, communication networks, and even financial transactions. By understanding the properties of flow networks, we can optimize these systems for efficiency and reliability. Flow networks find applications in a surprising variety of domains. Consider a transportation network where cities are nodes and roads are edges. The capacity of each road represents its traffic flow limit. Flow networks can help us optimize traffic flow, minimize congestion, and plan efficient routes. In the realm of computer networks, flow networks model data transmission. Routers act as nodes and communication links act as edges. Each link has a bandwidth capacity, limiting data transfer rates. Flow networks help optimize data routing, ensuring efficient and reliable communication. Even in seemingly unrelated fields like supply chain management, flow networks prove invaluable. Warehouses act as nodes and transportation routes act as edges. Each route has a capacity based on the number of trucks or shipping containers it can handle. Flow networks help optimize logistics, minimizing transportation costs and delivery times. These examples demonstrate the versatility of flow networks in modeling and solving real-world problems. By understanding the underlying principles, we can leverage these powerful tools to enhance efficiency, optimize resource allocation, and improve network performance across various domains. Section 4. The max flow problem, finding the bottleneck. The maximum flow problem lies at the heart of flow network analysis. It asks a fundamental question. What is the maximum possible flow that we can send from the source node to the sink node without exceeding the capacity of any edge? Answering this question has significant implications for optimizing network performance. Imagine a water distribution system. The source is a reservoir, the sink is a city, and the edges are pipelines with different capacities. Solving the maximum flow problem tells us the maximum amount of water we can deliver to the city. This information is crucial for urban planning and resource allocation. Determining the maximum flow involves finding the bottleneck of the network. The bottleneck is the edge or set of edges that limit the overall flow. Once we identified the bottleneck, we can focus on increasing its capacity to improve the network's overall performance. The maximum flow problem has numerous practical applications. For instance, in computer networks, it helps maximize data throughput, ensuring fast and reliable communication. In transportation networks, it optimizes traffic flow, reducing congestion and travel times. Section 5, Algorithms for Max Flow and Beyond. Over the years, computer scientists have developed clever algorithms to solve the maximum flow problem efficiently. One of the earliest and most fundamental is the Ford-Fulkerson algorithm. It works by repeatedly finding paths from the source to the sink with available capacity and increasing the flow along these paths until no more paths can be found. While the Ford-Fulkerson algorithm provides a solution, it can be inefficient for certain types of networks. To address this, more sophisticated algorithms like Edmonds-Karp and Dinnick's algorithm have been developed. These algorithms improve efficiency by strategically selecting paths to increase flow. Understanding these algorithms and their complexities is crucial for efficiently solving real-world problems. The choice of algorithm depends on the specific characteristics of the network and the desired trade-off between solution speed and accuracy. Moreover, the maximum flow problem is closely related to other graph theory concepts such as edge disjoint paths and the minimum cut problem. Edge disjoint paths refer to multiple paths that do not share any edges. The minimum cut problem seeks to find the smallest set of edges that, if removed, would disconnect the source from the sink. Interestingly, the maximum flow through a network is equal to the capacity of the minimum cut. This duality provides valuable insights into network structure and bottlenecks. In conclusion, mastering graph algorithms, particularly those related to flow networks and the maximum flow problem, is essential for tackling a wide range of real-world challenges. From optimizing transportation and communication networks to improving logistics and resource allocation, these algorithms provide powerful tools for enhancing efficiency, reliability, and performance across various domains.